if I have, you can write it as J0 plus, let me write K and K. This is just some symbol K. So my minus del K JK, I can multiply both sides by dqx, and I can integrate on both sides, right? So this would then this is a total divergence, and it can be converted into a surface integral, and this surface integral goes to 0 at infinite surface boundaries, or at infinite space-time boundaries. Okay, so what I get is this. This I could write as J0, okay, and I have made a mistake, del 0 J0, this is dqx dy dt of J0. I can take this out. So you find that if, for example, if my theory has a symmetry called as the gauge symmetry, which is an internal symmetry taking place at the same space-time point of the manifold, then this would lead me to the conjunct charges. This charge operator, this is here my J mu, so I can J mu is del L over del mu phi k, delta phi k, summation over k. So then I could, given the Lagrangian or the action of a theory, I can always calculate the charge operator of a theory. If I would do it for a real scalar field theory, I would of course get 0, because the real scalar is a charge neutral. Okay. However, if I would calculate it for a complex scalar field theory, I can do it in multiple ways, and you will always have that result. So, of course, as long as you express your result in terms of the fields phi, then that is the classical expression. So, but you can construct the corresponding, so charge you can calculate some phi dagger dot minus multiplied by some constant, okay? And this you could eventually, for example, for this theory, you could construct it to be n of A or B minus n of B K, because this constant that I am not citing here takes care of plus or minus overall plus or minus also. Okay, and so you can find out the charge of the particle A and B. It would be opposite to each other, and rest of the properties of these two particles A and B would be identical. Okay, so as long as we talk in terms of complex scalar field theory, I can always only say particle of the type A or particle of the type B. However, if I consider and do the same calculation for the Dirac spinor field, then of course my this charge operator would be, of course, like something like this. But there you could identify, or you could say that the electronic charge or charge of an electron or the charge of a positron. Okay, so the antiparticle would be a positron there, right? So all these things they stay the same for all these theories. And but in addition to, so this invariance under the gauge transformations or under the gauge symmetry leads to the conserved charge, which also is to be determined everywhere in all the theories. So this is one physically measurable or observable quantity, the charge. Okay, the classical charge is the classical level, and this is the quantized charge. Okay, and the other things are they happen because of the external symmetries. So space translation, invariance of a theory under space-time translation, or invariance of a theory under rotations of in the space-time. So you will immediately recollect the famous equation: energy momentum tensor del alpha T alpha beta equal to 0, and this would lead to del 0 T 0 beta equal to 0. These are, when I write it like that, then I am talking about densities. If you integrate it, so the full quantities you would construct always the full quantities by summing over the entire space. Okay, so like this, and now by this I want to say that this will T0 beta has 4 components, and what are these components? T0 0, T0 J, and what are these? This is H by C, and vector B. So this is the field energy, this is the field momentum. So for any theory, I can calculate at the classical level expressions for the field energy, expressions for the field momentum, and then I can go to the so-called second quantization, use my Fourier decomposition, Fourier modes in terms of the annihilation creation operators, and then I can calculate these quantities in terms of the annihilation and creation operators. Okay, and the field energy, as you know, has always to be positive definite. So in fact, we don't notice these problems as long as we are talking in terms of the bosonic fields. But about half a century ago, the all over the world, like right now, people do string theory, gravity theory, boson stars, neutron stars, cosmology, everything at the very leading level. At that time, it was the time of the development of quantum field theories, basics of quantum field theories. And then this problem of obtaining positive definite field energy for the Dirac-Spinner field was a big problem. And then this, now we know that they are the father figures of the quantum field theory, Jordan, Wigner, Dirac, all these guys. They invented the annihilation creation operators involved in the Dirac pocket space decomposition of the Dirac field. They have to be fermionic. Of course, we want them to describe fermions, but then they must be different than the bosons, and therefore they must have anti-commuting. And when you do that, then you get the right sign, and the field energy becomes positive definite. Okay, I would not be giving details of these calculations for any of these fields, but what is important is to know these results. And similarly, so here there are 4 conserved quantities: field energy and 3 components of the field momentum. Okay, these are 4 quantities. Charge operator is separate. These are 4. And similarly, if you have beta gamma, so this leads to and 0 beta gamma, and this guy is so I could call it by a different name. Let me call it n beta gamma. So this, as you see, is a matrix. Okay. So this would lead to the conservation of, this implies conservation of 6 quantities. Three components of angular momentum Nij, and this is antisymmetric, so minus Ngi, and three components of Lorentz boost. Operators, they would be N0 J equal to. So three components, 3 and